In the previous video, my bot was short circuited, so it's time to fix it. So let's get started. Yay, it's working now. Hello and what's up? In my previous video I've shown you how I have designed 3D wheels for my mesh solver bot, but as of now, as I've told you in my previous video, I don't have any 3D printer, and that's why I'm currently stuck with these kind of wheels, wooden wheels, which took me 3 hours to make and 6 hours to plan and a week of unslept nights. If you haven't checked that video yet, then go and check that video in the card server. It's kinda cool. You can find the whole series of this mesh solver bot. As you can see, it looks kinda cool, isn't it? In this video, I'm gonna show you the testing and also a little bit discuss about the PID algorithm. And if I show you the whole code and teach you the whole code, basically, then the video will be long as and that's why I cannot discuss the whole code in this video. Maybe I will make a separate video on the topic of PID control algorithm. Okay, but as of now, I will tell you, as I've told you in my previous video also, when I have shown you my basic code about this mesh solver bot, I've told you that we apply equal amount of forces in these two motors to actually stabilize the bot in our line. Suppose the line is here, so this sensor is lighted and all the sensors are not receiving any line. So basically what we do, we apply a force in this direction so that the bot aligns itself with the line to light up its middle sensors. Basically that's how it works. But suppose our bot is not that much out of line and it's around here, then also we apply that equal amount of force to correct it to the center. So what it does, basically, when our this sensor is lighted and when our this sensor is lighted, we apply equal amount of force for these two cases to align the bot itself in the line. So basically what it does is, suppose when the line is here, we apply a certain amount of force and it aligns itself with the line, it succeeds in aligning itself with the line. But when the same line comes, not the farthest sensor but one of those middle sensors that's still out of phase by a little bit in the right direction, it also applies that equal amount of force, which makes the bot tilt in another direction. So you can see we have now an opposite error, and we correct that using the same principle by applying equal amount of force like this, and this thing keeps on happening. Like when the line is here, we apply equal amount of force to correct itself here, and then when the line comes here, we apply opposite force to correct itself middle with the line. So it continues to do like this and never succeeds in aligning itself with the line in the straight way. And that's why we need that PID control algorithm. Now what PID algorithm does is it applies variable forces according to our sensors. So suppose it applies more force when the line is facing this sensor and apply less force when the line comes closer and closer and closer. The force gradually decreases as the line comes closer and closer and closer to the center line. Now what is the full form of PID? It's proportional integral derivative. It's kind of that kind of brain twisting name, but it exactly does that. Proportional, integral and derivative. It has three variables which is responsible for the proportional, integral and derivative control of these two motors. Now I will not go into detail into this proportional, integral and derivative. You can find in my code there is the little portion where we are applying the PID control algorithm. but basically I'm not going to discuss it today, but I'm going to discuss about those three P, I and D. That is about three constants, Kp, Ki and Kd. These three constants you have to tune your PID bot, and that's where the trouble comes in. Okay, so let me tell about these three variables. The first is the P, then the I, then the D. Okay, now the P is responsible for your correction, the oscillations. The D is responsible for bot stability, that means eliminating those oscillations, and that I is the number of overshoots. Now by the number of overshoots I mean when you are tuning your bot, the bot will not line up exactly. When your bot is aligning itself with the line, it will not exactly line up like this. It will eventually line up itself with the line by following some of those little oscillations. The first oscillation may be like this, then like this, and then it eventually dams out. So these are the number of overshoots you permit in your algorithm for your bot. That means if we put I equals 1, that means you permit one overshoot, and then the bot should line up. So now you can tell what is the desired value of this I. Can you? Obviously you can. It is 0 because we do not want any of those oscillations. We just need this kind of damping. So that's why we eventually put I equals 0, and you don't have to understand anything as of now. I have provided the code in the description below. You just have to tune those three variables, K, P, Ki and Kd. So the method I found on internet on Robotic Stack Exchange, how we should tune the PID and what is the actual method of tuning the PID, those three variables, because you can try those trial and error methods, but you obviously need a method to execute the trial and error method, isn't it? So in the Robotic Stack Exchange I found this method. I will put every link in the description down below. You can watch it whenever you want. So it says, first of all, we should set all gains to 0. That means Kp, Ki and Kd should all be 0, and then run your bot, and you will see it does nothing. It doesn't make any corrections with your line. It just goes like this. It doesn't care where the lines are. And then it says in point 2, increase the P value until you get steady oscillation to a disturbance. That means when you put your bot in your line, then it should cause a steady oscillation like this. I loosen the LEDs. Then in step 3, you should increase the D value until the oscillations goes away. And this is the main step you have to proceed going. I mean, increase the P until you get an oscillation, then increase the D until the oscillation goes away, and then again increase the P until you again get oscillations, and then again increase the D until it's fade away. Like this, you have to repeat this procedure again and again and again until you get a stable value. So that thing gone. That's, we talked about P and D. What about the I? As I've told you earlier, I is responsible for how many oscillations we permit before it comes to rest. So we will put it to 0, or you can also put it to some minimum values. You can tune it by yourself. I have put it 0. Okay, so there goes our algorithm, and you can find in the code there is another definable variable I have put is the maximum speed. The maximum speed is where you set the correction speed, maximum correction speed. Like if when the robot bot is like this, it will apply that much amount of force to correct itself. Now what is the maximum? Obviously it's a 8-bit value, that is 255. So you can put the maximum as 255. I have put it 200 because 255 sometimes go crazy for me and the bot just jumps out of the track. So that's why I put it to 200. Okay, you can put whatever you want. These are the tunable variables I have told you. And also there is another variable. The variable was also in my basics code, but now the variable does something different. That is the O speed, or it is the initial motor speed. Now where your initial motor will start and then the correction will apply to your motors like this and that. So you can tweak with that correction core speed too. It's the initial motor speed. So let's now see how it does. In my track, I have printed this track in banner or whatever it's called. It's called flex printing. So you can grab your own track and print it, design in Photoshop and print it out. I've also put my track in the description down below. If you want, comment down below in the comment section. So I will put my own track. So I will show you how my bot performs with the basic code and the PID code. Now let's run the basic code first. As you can see, it performs like a Now let's try the PID code. As you can see, the PID actually turns pretty well, but still it's not accurate, and that's because of my sensors. These sensors, as I've told you, are not pretty accurate. So I will tell about all of my bots cons in another video. Okay, I don't want to make this video long as What? You think this is slow? Then watch this. Obviously this is fast, but you also need accuracy, and that is the main thing. Speed and accuracy both are dependent on this, and my bot is heavy as It has lot of inertia and it skids away, drifts away of the track, which I cannot fix because my bot is heavy. Now as you can see, the PID actually does a pretty good job, actually better than the basic code obviously, but as I've told you, you need a straight line to actually see how it performs with those oscillations. Now let's see in my straight track, and you can also see the 90-degree turns and also how it performs the basic and PID code. Now I will not talk in these videos, I will only put the settings I have put, and you will see how the bot performs. Let's get started. now the PID algorithm. Let's see how it does. Piece of shit. The f. Piece of. Obviously it will be fast, but I have to tweak with the code because I haven't designed the code to follow this kind of straight lines. Now, as you have seen, the PID control algorithm is not doing so well. My basic code is good. Why is that so? I have to fix it now. Obviously, now the initial place speed is 100, which is very low than 255. So let's see what it does. It will result in slower bot movement, but the oscillation should go away. Let's see what it does. So slow. Let's see, the bot is stable now. Yes, it can kind of damp those oscillations. See now. See, the oscillations get eliminated. This is what PID does. See, again the oscillations are eliminated. It's smooth. See? Wow. But it's too slow. See, it kind of eliminates the oscillations now. 2 or 3 overshoots, and then it damps. 1 or 2 overshoot, and then it damps all the oscillations. See? Now let's count how many overshoot it does. 1, 2, 3, 4. Actually 4. 1, 2, 3. Now it's 0. It's kind of cool. See? It's smooth. Smooth as f. But I have to increase the speed now. Let's see what I can do with the code. After increasing, it may change. Let's see what it does. Oh yeah, it can eliminate the oscillation still, which is kind of good, but not always. Again it oscillates like See, trouble of tuning the PID. It kind of settles though, kind of dumb, better than the previous runs, but still you can see those oscillations which I have to eliminate. How can I though? Let's try 110. Speed is 110 now. Yeah, obviously better than 120. And also it's not too slow. Yeah, it kind of does. It kind of does what it's supposed to. See, it faced the oscillation in about 4 or 5. It actually damps those oscillations in about maybe 3 or 4 overshoots. See, now it's only one overshoot. It's kind of cool. No overshoots at all. One, two, three, four. Actually, it is not able to dampen it now. 1, 2, 3, around 3.5. And as you can see, after a lot on tuning, you can see now it actually kind of performs well, but it's too slow. And that's because I have put the initial motor speed as around 100 and 110 to actually, I think the problem is with my bot's weight. It cannot handle that much amount of weight. As you can see, in lower speeds it does pretty well in correcting those oscillations, and you can see it's quite stable. But as soon as you increase the speed, the bot's like, it's because of its weight maybe. So now I will put same settings and let's put in my zigzag track and let's see how it does.